Okay, folks, good morning. Just a reminder about your grades. I finally uploaded that Excel file on Blackboard. So please take a look. Your grades are all there. And as promised, only the last four digits of your student ID shows. However, if the first letter of the last four letters is a 0, like your student ID, the last four digits are like 0357, only 357 shows. So if you see a three-digit number, the left one is a 0, and that's like an Excel thing that it does. I couldn't really get rid of it. All right. So that was about the grades. We are going to have the third quiz today towards the end of the class. And no, the quiz has nothing to do with the government shutdown. We're still going to have the quiz today. Any questions regarding Bock, Boost, or anything that we have covered so far? Any questions? Last chance for questions? Okay, so no questions. Good. So we are still in chapter, I guess, 6. And this chapter covers DC to DC converters, non-isolated DC to DC converters. And we are going to see later on what isolated and non-isolated converters are. So the first converter that we analyzed was this guy over here, which is the boost converter. It has a switch on the input side and an inductor on the output side and a diode in between. And we found the voltage transfer ratio of this converter to be V out over Vin is just the duty cycle. And duty cycle is a parameter that we or the controller can control in a sense that we can adjust the value of the duty cycle to be at 60% or 70% or 50% is adjustable. So we can technically adjust the value of the output voltage. And because the duty cycle, as it is defined, it is always between 0 and 1, that's the indication over here is that your output voltage is always between 0 and the input voltage. It can never get larger than that. So you're always, in this topology, stepping down your voltage. Then we looked at another topology, kind of continued the same, did the same analysis for this one, which is called the boost converter. The components are the same. The difference is on the input side, now we have the inductor. On the output side, we have a diode. And in between, we have the switch. We derived the voltage transfer ratio of this topology, which is V out over Vin, is 1 over 1 minus D, D being the duty cycle again. And again, because the duty cycle is between 0 and 1, you can argue that your output voltage is always greater than your input voltage. So that's why it's called a boost converter. And we are going to actually do some more analysis today on this topology. For instance, take a look at what is the equation that we have for the maximum value of the inductor current, the minimum value of the inductor current, and then from there we can find the right size for our inductor and later on the right size for our capacitor. However, before that, I just wanted to mention, bring this chart to your attention. And if you plot basically, let me see. So we just mentioned that V out over Vn is 1 over 1 minus D. D is the duty cycle. So if you plot this, you're going to get at duty cycle equals to 0, you get 1. Your gain is 1. And as you increase the value of the duty cycle, your gain increases. And as you get closer to 1 as your duty cycle, you can see your gain gets to infinity, ideally. But practically, that doesn't happen. Practically, what happens is, we have analyzed the system under the assumption that there is no losses in the system. But practically, there are losses in the system. So if you build a converter in the lab and test it, as your duty cycle gets close to 100%, your output voltage is going to actually go down because there is losses in the system. So just looking at this equation, I can say I can convert 20 volts to 1,000 volts. But practically, you cannot. And just bear in mind, in all of these converters that we analyze, it is not a good idea to keep the duty cycle between 0 and 20% or maybe between 80 and 100%. So a more reasonable range for the duty cycle is somewhere around here. All right? if you push the value of the duty cycle beyond these boundaries, you're going to very extreme cases. For instance, you may go to the discontinuous conduction mode, or you may have a lot of ripple in your inductor current, you know, those kind of things, or your efficiency is going to basically get really, really bad. So in a practical case, a good number for the duty cycle is always bound between maybe 20% and 80%, maybe 25% and 75%, that kind of range. All right, once we are done with the boost converter, then we are going to get into another topology, which is the Bock boost converter, and we are going to see, you know, why it is called like that, and when we get there. All right. So this is what we did last time. We looked at the boost topology. We kind of drew some of the important waveforms, and the waveform that we are going to start today with is this one. The current that passes through the diode. So if you look at the Bock converter, the inductor, which has the continuous current, feeds the R and the C, the output side, this capacitor and this resistor. Over here, we have the diode replacing the inductor. So we have to look at the current of this diode to be able to actually see, for instance, how much power is delivered to the load, those kind of things. And the current of the diode is easy to obtain. In the first mode, between 0 and dt, the current is 0 simply because the diode is reversed bias and it is not conducting. And in the second part, or in the second mode, it is on and is actually following the inductor current waveform. So this is the waveform you will get for the inductor current. So this maximum value for the diode current is the same as the maximum value for the inductor current, and this minimum value for the inductor current is the same as this point over here. They are basically identical, assuming everything is ideal. All right. So we have this current waveform for the diode. So let me move to the newer one. So we have this waveform for the inductor. Oops, I don't know why I cannot pick colors today. Oops, look. Still black. I don't know. Let's see. Somehow today is a black and white kind of a day. It's because of the government shutdown or something. But anyway. I have this waveform for the diode current, and I am trying to relate this to my load parameters, for instance, the load current, things like that. And the reason that I want to do that is ultimately I want to find an expression for this is where I'm trying to get an expression for Imax and an expression for Imin, okay? And using the Imin to basically, the expression for Imin to find the right value for my inductor. As you can see, L appears here. All right, so let's do that. Let me see if I can fix this. None of these menus are available. I click on them. Let me just close. It has something to do with this. All right. Okay. It's not working the way it's supposed to be working. Anyway, so let's do that. Let's take a look at the average value of this current. Why are we interested in the average value of this current? Is the reason is at any given time. Oops, changed. The current of the diode. If I apply KCL over here, I can say the current is feeding the cap and the resistor. So at any given time, is the current of the cap plus the current of the resistor. All right? And the current of the cap on average is 0, and the reason is the voltage across the cap is a periodic waveform. So if I take the average of these equations, this is relatively thick. And please note the symbol that I'm using to, this is the symbol for averaging, by the way. And I guess you have seen this before. All right. So my argument is this is 0. Okay, so on average, the diode current and the load current are the same. So if I have the waveform for the diode current, all I can do is I can actually find the average value of the waveform, and from there I can use this equation to relate the load value and a bunch of the rest of the parameters in the system. So if you do so, okay, so I'm looking at this trapezoid and I'm trying to find the average value of this current. Okay, the area of the trapezoid, which is I max plus I min over 2 times duration, which is t minus dt, over, I'm doing this averaging. Always remember, you're doing averaging over the entire period, so I have to divide this by the entire period. And this has to be, so this is the average value of this waveform, or the diode current. This has to be the average value of the load current. And load current, the average value and the instantaneous values are almost the same, because load is basically the voltage that appears across the load is just a constant, almost a constant DC source. So this has to be V out over R. All right? So if you simplify this, you can find an expression for I max plus I min. Okay? Which is twice the output voltage over 1 minus the duty cycle over the value of the load. All right? Now, sometimes in these equations you prefer to have only the output voltage, sometimes only the input voltage. It doesn't matter, like over here. In order to get rid of this expression for the output voltage, I am writing it in terms of the input voltage. Remember, in the boost converter, V out over V in is 1 over 1 minus D. So whenever I want to get rid of V out, I can replace it with V in over 1 minus D. And that's what I've done over here. So you end up having an expression like this. I max plus I min equals twice the input voltage over 1 minus duty cycle squared over R. And I've labeled this equation number 6. And previously, when we were analyzing this system in mode number 1, when we had an expression for delta IL, which was defined to be I max minus I min, we had this expression of it's equal to V in over L times dt, or V in minus V out over L times 1 minus dt. But we are going to use this one that in which only V in appears. So we had two expressions for delta IL. We choose the one in which only V in appears, not V out. So I have these two expressions. So I have two parameters that I'm looking for, I max and I min, and I have two independent equations, so I can just solve these two equations and find an expression for I max and an expression for I min. So here it is. I max turns out to be this expression, V in over 1 minus D squared times R, plus half of the ripple, which is V in dt over twice the inductor. And I min is basically the same expression, only with a negative sign. All right? Okay. And now that we have I max, now that you have I min, you can find the average value of the inductor current. So remember, the inductor current waveform is a kind of a triangular symmetric waveform. So if I have the maximum value, if I have the minimum value, I can just take the average of these two and claim that that is the average value of the inductor current, which is like half the way between I max and I min. So, okay, the average value of the inductor current is the maximum value of the inductor value, the current, plus the minimum value of the inductor current over 2. I have I max here, I place it from here. I have I min, I place it over here. These two terms just cancel out each other because they are going to be added with each other and they are opposing each other. And then the division by 2 only gives me this expression. Okay? On average, the inductor current is Vn over 1 minus d squared times R. And that turns out to be your input current as well, because the inductor is on the input side. If you remember, the topology looks like, let me see. So as you can remember, the inductor current and the input current are basically the same. All right. Now there is another way of actually concluding this, and that is by comparing the input power and the output power. This is an ideal converter, so input power and output power, they're both the same. On the input side, we have a DC source, so the input power is Vin, which is a DC voltage source value, times the average value of the source current, which is IL. So that gives me this expression. On the output side, again, we have almost a DC voltage level, which is V out. If I square that and divide it by R, that gives me the output power. And also, on one side, I have Vin. On the other side, I have V out. If I want to get rid of all of the V outs, I can just replace them with Vn over 1 minus D. So in the end, you will end up the same with the same equation, basically. So IL is Vn over 1 minus D squared times R, which resembles the equation for transformers. Remember, just assume a system like this. Okay, let's say you have a resistor on the other side of a transformer, and the voltage transfer ratio of this transformer is 1 to 1 minus 1 over D. Okay, something like that. So if you want to transfer the resistor to the other side, the impedance to the other side, it will be multiplied by the turns ratio of the transformer. And here you can see R has been multiplied by 1 minus D squared. Okay, so this is exactly like you can imagine the Bock or the boost converters like DC transformers. So if you want to look at the input impedance or the input power consumed over here, you can reflect the load that is on the output side to the input side, assuming that this is more like a DC transformer. So you will get something like this. Okay, the value of the load is being multiplied by the square value of the turns ratio, something like that. All right. So these are good equations. The most important one is this guy over here, number 8, that we are going to use to find the right size for our inductor. But also the average value of the inductor current equation is very important. A lot of times, lots of parameters are missing in the exam that you are, or the quiz problem that you have. But this comes in a very handy equation to solve and find the missing parameter. All right. So let's use equation number 8 to find the right size for our inductor. So remember, all of this analysis was under the assumption that the converter is operating under CCM, continuous conduction mode. Okay? Meaning that the inductor current should be positive at any given time, meaning that the minimum value of the inductor current should be above the 0 level. Okay? So we had an expression for Imin, and that was Vn over 1 minus D squared R minus Vn dt over twice the inductor. So this guy should be positive. And by the way, this expression may look a little bit complicated and scary, but if you look, this is average value of IL, and this part is delta IL over 2. Okay? Similar to the Bock converter. Again, at any given time, at any given converter, the minimum value of the inductor current is its average minus half of its ripple. All right. So I can take, I can further simplify this equation and end up here. In order for my minimum value to be positive, the inductor should be greater than the duty cycle times 1 minus duty cycle squared times load value divided by twice the frequency. And we see a similar trend is happening here. Again, frequency happens in the denominator over here, meaning that increasing the switching frequency will give you the option of choosing a smaller inductor. Okay? Now, this equation is a little bit tricky. Remember, we always want to maximize Remember, operating conditions are variable. For instance, your load may be variable. Your duty cycle may be variable, for instance, because the output voltage is variable or the input voltage is variable, or maybe they're both variable. So you always want to maximize this given the operating conditions, and then make sure your L is even greater than that maximum value, okay? However, maximizing this is just by looking at it. You cannot identify, should I put the maximum value of the duty cycle to maximize this expression or the minimum value of the duty cycle, and the answer is neither one of them. If you plot just d times 1 minus d squared, you will get an expression like this. You will get a curve like this. All right? So please remember, if your duty cycle has a range from 0 to 1, the maximum value happens somewhere around here, for instance. All right. So in the design, you have to be careful about this curve, where my duty cycle is changing from where to where, and then what would be the corresponding maximum value for d times 1 minus d squared. Then I have to put maximum value of r over here, and division by twice the frequency, no problem. 2 is constant, the switching frequency is constant. So please remember, maximize this expression using this curve over here, and then use the maximum value of r, and then the rest is just easy to figure out. Okay. And we have an example to actually use this. All right, here is our example. We have a boost converter. The switching frequency is set to be 50 kilohertz, constant. The load is 50 ohms. The input voltage is 12 volts. And the inductor has already been chosen to be 70 microhenries, okay? And also the output voltage is supposed to be 15 volts. All right. First question, is the converter operating under continuous conduction mode of operation? Okay. So if you have a question like that, you have to basically check the validity of this expression over here. Is my L larger than that expression or not? So I'm going to calculate that expression basically. All right. So I'm trying to calculate d times 1 minus d squared over twice the frequency times r. I don't have the value of the duty cycle. However, the input voltage and the output voltages are given. You can easily find the duty cycle. So remember, V out over Vn is 1 over 1 minus d. Therefore, if you want to calculate d, d would be 1 minus Vn minus V out. Okay. Vn is 12, V out is 15, so that gives me 0.8. Then 1 minus 0.8 will give me 0.2. So duty cycle is 20%. All right. So for this duty cycle, we place 0.2, same value here. And the frequency is 50,000, and the load value is 50. Okay? So altogether, if you punch in the numbers, you are going to realize that that expression, the numerical value of that expression is 64 times 10 to the power of negative 6. And as it turns out, our inductor, which is 70 micro, is greater than that 64. So that means you are operating under continuous conduction mode. So the answer to that question is yes. The converter is operating at continuous conduction mode. Okay, so this part was easy. And please, from now on, whenever you are analyzing a circuit, your first question always should be like that from yourself. The thing that you ask yourself, maybe it's not even, the question is not even mentioned in the problem, but you always have to ask it from yourself. Is this converter operating at CCM or is it operating at DCM? All right, so this case, it was operating at CCM. And then part B is asking about find an output voltage range where the converter does not operate in CCM. Okay. All right. So this is like a case that you want to have a variable. Let's say you want to build a power supply, for instance, and you want to have a variable output voltage. And in order to achieve variability in your output voltage, you basically tune the value of your duty cycle. Okay. However, if you mess around with the value of your duty cycle, you're going to realize that there are times that your converter will not operate under CCM. So we want to take a look at that. All right. So in order to find a boundary between basically CCM and DCM, the boundary happens when L is exactly equal to, so the boundary is, again, I don't know about the word boundary. Is there an A here or an E? But anyway, if the inductor is equal to D times 1 minus D squared times R over twice the frequency, then I'm at the boundary of CCM or DCM. If L is a little larger than this, I'm in CCM. If L is a little smaller than this, then I am in DCM. So that's where I'm trying to find a boundary. Okay. And I already know what L has been chosen, which was 70 microhenries. Duty cycle is a variable now because the output voltage is variable. So please do not put 2.2 anymore. R is, so this is 70 micro. R is 50 ohms. And the switching frequency is 50,000. Okay. Other than that, we don't have we are using the duty cycle as a parameter here, basically. So this we are going to end up an expression like this, that D times 1 minus D squared is 0.14. Whenever we find a D that satisfies this expression, that means that particular D corresponds to the specific boundary between DCM and CCM. Now, this is a third order system, third order equation. We have three solutions. One of them is not an option because it gives us a duty cycle that is greater than 1, like here it's 1.3. So these are the viable solutions, okay? All right. So you kind of, if you plot this, this is the situation that is going on basically. So what's happening here is this doesn't look like, this doesn't have a, okay, so what I'm here plotting is D times 1 minus D squared over twice the frequency times R. And I'm using D as my variable, varying from 0 to 1. And I want to see under what circumstances this expression is crossing the value of the inductor, which is 70 micro. All right? Okay. If I end up in this basically region, in this region you can see L is smaller than expression. So here it's corresponding to DCM. But here my L is larger, so I am in CCM as well as here. All right? So I already solved this equation and found two numbers. One of them is obviously my drawing over here is not up to scale, but 0.247, and the other one is 0.428. All right. So as long as I stay out of these boundaries, I'm good. I'm operating under CCM. Otherwise, the converter is operating under a DCM. Okay. So I know the boundary values for the duty cycle, and then I can plug them into the equation of V out over V in is 1 over 1 minus D. So one time for D I place 0.247, and the second time I place 0.428 to find the corresponding output voltages. All right? And that's what I'm doing over here. Once I place this answer to the equation, second time I place this answer to the equation. The first one gives me an output voltage of 15.9 volts. The second one gives me an output voltage of 20.9 volts. If I stay out of these, I am in CCM, otherwise you are in DCM. So if your output voltage is between, let's say you are doing this power supply thing, if you want to have an output voltage that is between 15.9 to 20.9, your converter is going to operate under CCM. Otherwise, your converter is operating under DCM. So unfortunately for the boost converter, the CCM, DCM boundaries are a little bit more complicated simply because this expression over here is a little bit complicated. We have D times 1 minus D squared. All right, and that makes things a little bit complicated. If you compare it against the Bock topology, if I can find it, in the Bock topology things were much, much easier. It was only 1 minus D over twice the frequency times R, something like that. So you can see things are going to get a little bit complicated here because we have D multiplied by 1 minus D squared, and finding the maximum value of this expression is not very trivial. All right, any questions? So this is how you find the range or the area in which you are operating under CCM. So what we did was we started with the waveform of the diode current, and we ended up finding an expression for the minimum value of the inductor current, and that expression led to a design equation, which is a very, very important design equation to size the required inductor. So this is a very, very important equation. All right. So we know how to design the inductor now. So the next step is, how are we going to design, or the next question is, how are we going to design the capacitor? So that is actually where the rest of the discussion comes in. All right. In order to find the capacitor, the similar thing that we did for the Bock converter, we have to find the current waveform of the capacitor first, and then look at its ripple, and then find the peak-to-peak ripple of the cap, and then find an expression for the cap. Okay. So we are still focusing on the output side of the topology. So we have this diode on the output side feeding this cap and this resistor, which is our load. All right. We found the current waveform for the diode to be a kind of a trapezoid like this between dt and t, and it starts from a maximum value and ramps down to a minimum value, then jumps back to 0. And so remember, we have the diode current is the cap current plus the load current. All right, and that gives me, if I'm interested in finding the cap current, that is the diode current minus the load current. All right, but also from the previous section, we remember that the load current is the average value of the diode current. So technically, you find the average value of your signal and then subtract it from the original signal, and that's your cap current. So that means I'm shifting down this ID waveform to a level so that it would have an average value of 0. So IC is exactly like ID, only shifted down so that its average value is 0. All right? All right. So you can see in the first mode, your cap is exposed to some negative current, and it is being discharged. In the second mode, the cap is exposed to some positive current, therefore it's getting charged. And on average, it's neither getting charged nor discharged, because on average the signal is 0. All right, so if I want to plot the cap voltage, remember cap voltage is the integration of the cap current, right, plus some initial value, right? So let me write the complete equation. So integrate the cap current, then divide it by the value of the cap, then add the initial value, and that's actually our waveform. So if you do so, you are going to see a waveform like this. All right, for your cap. In the first mode, the cap is being discharged with a constant current, so its voltage is just ramping down like a straight line. In the second mode, the current is not constant, it has its own ramp, and if you integrate a ramp, you're going to get a second order equation. So that's why I have a kind of a straight line over here, because the current is constant, just constant at this level. And then over here, current is a line, therefore integration of a line gives me a second order kind of a curve. So that's actually your voltage of the output capacitor. Okay. So you can observe that the voltage is actually fluctuating between two boundaries. And I just label that to be delta V out, the peak-to-peak ripple of the output voltage. So delta V out is the peak-to-peak ripple of the output voltage. All right. And I'm trying to find this peak-to-peak ripple. And hopefully that's going to be related to the cap. And finally, I get an expression for the value of the cap. All right. In order to find this, again, we go back to that very original equation of in capacitors, electric charge is proportional with the voltage, and the coefficient of proportionality is the cap value. Or changes in the charge causes changes in the voltage. All right? Okay. I'm trying to track down these changes in the voltage, for instance, from here to here, so I have to track down how much charge has been taken out of the cap, and that is this area over here. All right, so this is my delta Q. All right, so the other thing that you guys have to remember is electric charge is the integration of electric current. All right, so if I have a particular current waveform, the area underneath that curve is actually my electric charge. So this delta Q comes from this square, this area over here, which is V out over R times dt is C times delta V out. All right? All right. So remember, we shifted things down. All I have to mention over here is this height is V out over R. Now why is that? Because we shifted the signal by IR, and IR is V out over R. So this was originally at 0. Now we shifted it down by IR, which is V out over R. So the new value is negative, basically V out over R. And we're only caring about the area. We don't care about the negative polarity. All right? So there you go. You have a very simple expression for your cap voltage. The only parameter that you have to get rid of is nothing. You just have to rearrange things, and you end up having this expression. So delta V out, which is an indication of how much ripple appears across your output voltage, divided by V out, which is the DC value of the output voltage. And remember, delta V out is very small, V out is very large. That equals the duty cycle over R over C, the value of the cap, over F, the frequency. So this gives you an indication of how much capacitance you need. So you can actually choose your cap to be larger than this expression. All right? Usually the customer comes in and says, I need a converter with a delta V out of plus, or I don't know, let me not write it plus or minus, it's going to be a little confusing. Let's say 20 millivolts and a V out of 30 volts. So you have delta V out, you have V out. All you have to do is just divide them by each other. Then the rest of the parameters are determined, like the duty cycle depends on what your Vn is, R depending on how much power you're consuming, and F is usually around 100 kilohertz. Again, the same trend. Frequency appears in the denominator here, indicating that the larger the frequency, the smaller capacitor we need, which is a good thing. All right. Any questions so far?
What is the significance of this delta VO by VO max?
The significance. Okay, the question is, what is the significance of this delta V out, right?
No, delta VO by VO max. in that?
Oh, over here. If you have a case, okay, the question is where is this max coming from? If you have a case where your V out is variable, you have to make sure that you're maximizing delta V out over V out. Okay? Or maybe I should put the minimum value over here, I think. No. Hold on. This should be V out max. All right? So if you find yourself in a case that you want to design a system that have a variable output voltage, you have to consider the maximum value of your output voltage and put it over here, because if you put the maximum value of your output voltage, you're kind of maximizing this expression. And then make sure C is even larger than that maximum value. All right. Good question. Yeah. Okay, other questions? All right. So we are going to have a numerical example. Using these two equations, one gives us the right size for the inductor over here. The other one gives us the right size for the cap over here. And there you go. You are in business. Okay. So we have been asked to design a converter which has an input voltage of 12. Let's say you have, for instance, a car battery kind of a thing. And so your input voltage is 12 volts. The output voltage is 30 volts. You're trying to boost up the voltage. And you have been asked to design the system so that it operates under continuous conduction mode. And delta V out is supposed to be less than 1% of V out, which is the DC value of the output voltage. Or it could have been expressed in this way. Delta V out over V out is supposed to be less than 1%. All right? And the load, which is an indication of how much power is consumed, is 50 ohms. And again, this example comes from the Bock, so we have two actually frequencies. Okay, the original frequency in the Bock was 25 kilohertz, which is relatively low. And then I chose 100 kilohertz, and we are going to actually be able to compare the numbers. So everything that I write in red is associated with, first it is associated with this 25 kilohertz of switching frequency. Okay. So in all of these equations, you need the value of the duty cycle. And we don't have it, but we can easily find it. Remember, V out over V in is 1 over 1 minus D, or D is 1 minus V in over V out. This expression over here. And in order to convert 12 volts to 30 volts, you should find a duty cycle that is, you should apply a duty cycle that is 60%. Okay, so we have the duty cycle. Now from equation 10 that we had earlier, which gave us the right size for the inductor, L has to be, the inductor should be larger than D times 1 minus D squared over R twice, divided by twice the frequency. We pretty much have all the numbers. Duty cycle has to be at 0.6, load is 50, and switching frequency is 25 kilohertz. All right? So you just plug in the numbers, you find out that your L should be larger than 96 microhenries. As long as you choose this inductor for your converter, you're guaranteed to operate at CCM. And usually you go a little bit beyond that because the parameters in the system may change. There might be, aging effect. There might be temperature effects. So you don't stick with 96 micro. You go with like maybe 20% above that. So you choose, or a simple reason could be you searched, you just searched the market and there was not a particular inductor that was exactly 96 microhenries, but you could easily find a 100 at a cheap price. You could easily find 120 microhenries. So you can choose L to be 120. Anything larger than this is fine. All right. Now, if you choose the switching frequency to be 100 kilohertz, all you have to do this time, instead of F being 25,000, you have to put F being 100,000, which is 4 times more. Therefore, the inductor that you need is 4 times smaller. So you have kind of quadrupled your switching frequency, and your inductor shrunk 4 times smaller. So L has to be greater, in this second case, L has to be greater than 24 micro. So you can choose L to be 40. All right. So you increase the switching frequency, your size for the inductor got smaller. That means your converter is going to be smaller, but at the same time, you may actually have more losses in the system because there is more switching losses because the switching frequency is higher. All right. So this was about finding the L value. What about the capacitor value? Okay. So now we are using equation number 11 over here. Delta V out over V out is given to us. It's supposed to be less than 1%. And we have D, we have R, we have F. All that is missing is C. So C has to be larger than D over R over F over delta V out over V out. And duty cycle was 0.6. Load was 50. I'm sorry, I should write in red now. So this is 0.6. Load is 50 ohms. Switching frequency is 25 kilohertz, and delta V out over V out is 1%, which is 1 over 100. All right. So if you choose your cap to be larger than 48 microfarads, you are in business. Your ripple is less than 1% of the DC value of your output voltage, and then, for instance, you want to choose something a little larger than this. For instance, to be 60 microfarads. I don't think you can find a 60 microfarad capacitor in the market. Maybe 100 microfarad would be the closest option that you have. I don't really remember the range right now. And the second try, you choose a switching frequency of 100 kilohertz. So the only difference is this time you put 100,000 over here. So your cap is also going to get 4 times smaller. Only 12 microfarad of cap is needed. So you can choose anything above that. For instance, assuming that this is available in the market, 24 microfarad or maybe 47 microfarad is something that is available in the market. All right. So this is how you choose the value of L and then choose the value of the cap. Now remember, in the Bock converter, you first had to design L because L kind of appeared in this capacitor equation. But over here, they are kind of independent of each other, which is a good thing over here. So if you mess one of them up, the second one is not necessarily going to be messed up. Okay, any questions? All right. So what I'm going to do next is we are going to move on to the next topology, which is called the Bock boost topology. And basically, let me just draw all these 3 topologies next to each other so you guys have a comparison, frame of comparison. So for Bock, this was the system. This time I'm drawing them using IGBTs. All right, this was our Bock topology. Then we analyzed the boost topology. All right. Now there's a third option, which is called the Bock boost. And this is what it looks like. Oops. All right. All right, so this is our Bock boost. We are kind of rotating things around, and the switch is on the input side, the diode is on the output side, and the inductor is like in between. Okay? It is very, very important to consider this change of polarity over here. All right? As it turns out, the Bock boost topology always gives you a voltage that is negative with respect to your ground. So if I assume, like in the Bock topology, if this is my ground and my source is positive with respect to ground, my output voltage is also going to be positive with respect to this ground. Same story for the Bock boost, but for the boost. But for the last one, which is the Bock boost, if your input source is positive with respect to the ground, your output voltage is going to be negative with respect to the ground. So, if you open up different books, you're going to see different polarities. In some books, they assume that this is the polarity of the output voltage, but in all of the equations that they have, there's a negative sign appearing. Now, in order to get rid of that negative sign, I just assume that, to begin with, the polarity of the output voltage is reversed, and therefore you can get rid of all of those negative signs. So, my notes may not even be consistent with the assumption that I'm making, so I have to pretty much rewrite all of these equations over here. In the end, they're all the same. The whole thing is you end up having something like this: V out over V in D over 1 minus D. And in some books, because they have chosen the different polarity, they also have a negative sign over here, but we are not going to do that. We're just going to keep it simple, no negative signs, just D over 1 minus D. And you can see why it is called the Bock boost topology, because if you multiply, remember for the Bock, we had D. For the Bock boost, we had 1 over 1 minus D. And over here we have D times 1 over 1 minus. It's like if you multiply this by this, if you multiply them, you will end up something like this. So that's why it's called the Bock boost topology. It has a little of a Bock effect in it. It has a little of a boost effect in it. So it's like a combination of the two topologies. Now, the fact that the polarity of the output voltage is reverse the polarity of the input voltage, sometimes it's a bad thing, sometimes it's a good thing. You know, sometimes you want to create some negative voltage, so this is a very good way of doing that. Also, I can redraw this topology this way. All right, this is the same topology, just redraw it differently. To basically point out that using the Bock boost topology, we can actually transfer energy from elements that are placed in series with each other. And what is the application for that? For instance, you have a string of batteries. Okay? All right, for instance, let's say you have a hybrid vehicle. It has a battery in it. It has a battery pack, and if you open up the pack, you're going to see lots of battery cells placed in series with each other. And there is this concept, especially for lithium-ion batteries, of charge equalization. So you want to get charge from one cell and send it to the other cell to equalize the charge between the cells. And Bock boost converter is a very good, solution for that. You can just, using the Bock boost converter, you can discharge the battery and send charge over here. Then you can have another one and discharge this one and send it to you. So you can actually transfer charge from one cell to the adjacent cell using the Bock boost topology. So that's a good thing. All right. So we are going to analyze the converter in the very same fashion that we have analyzed the Bock and boost topologies. We make a bunch of assumptions. For instance, we are analyzing the system under steady state conditions. All of the components are ideal. And we are analyzing the system under continuous conduction mode. That means the minimum value of the inductor current is positive. The output capacitor is very large, meaning that the ripple in the output voltage can be neglected. And the input power and output power are the same, 100% efficiency. And switching transients are neglected, meaning that as soon as you want to turn the switch on, it is on. There is no transient time happening in between. And similar to the previous cases, we have one switch in the system, and the control command that is applied to the gate of that switch is on at the beginning of the cycle, and then it is off for the remaining portion of the cycle, okay? And in order to kind of note or identify the duration that the switch is on, we define this duty cycle, which is the on time over one period. So if this is one switching period, this ends up being D times T. Okay, the time that you turn the switch off, or the duration that you turn the switch, keep the switch on. Similar to the previous cases, we have two modes. Mode number one, switch on, and later we are going to see that the diode is off in this mode. And mode number two, switch turns off, and similar to the previous cases, diode is going to be on during this mode. All right. So let's consider mode one. In this mode, the switch has been turned on by the controller. The duration of this mode is from 0 to dt, this part. And we have to find out what's happening to the diode, okay? So if you consider this polarity, let me just revise all of these notes with this red ink. All right. If you consider this polarity for the output voltage, or maybe I should just write it over here to make it less confusing, okay? This is just to start from here. Oops. Okay. Right now, because I have already analyzed the system, I know that the polarity that appears in my output voltage is positive in the bottom, negative on top. But later on, you have to double check that, okay? In the end, you have to make sure this was the right assumption. So far, we go with this assumption, but in the end, we have to verify that. Okay. So we are in mode one. Switch is on. Okay. I want to see what's happening to the diode if the switch is on. So let's take a look. Switch is on. I replaced it with a short circuit. I don't know what's happening to the diode. And here's my output voltage. Okay? So apply KVL around this loop to find the voltage drop across the diode. Always from anode to cathode. And this turns out to be, okay, so let me write KVL and do that. So negative VN, negative VD, negative Vout equals 0. So VD is negative VN, negative Vout, okay? Assuming the polarity that I have chosen is correct and Vout is a positive value, Vn is also a positive value, so this whole thing is a negative thing. If Vout is really positive. So later on I have to check that. But so far, if I go with the assumption that Vout in this polarity is positive, I will end up having, as soon as I turn the switch on, I will end up applying a negative voltage across the diode. So V diode is negative, therefore diode is off. Okay? So technically your system is reduced to this diagram. On the input side, we have a DC source charging up an inductor, and the diode is off, and on the output side, we have a capacitor providing electric current to the load, and it doesn't matter if you consider this line or not, basically. So it's like the input and output are kind of isolated from each other. All right, I'm going to stop here. So we're going to continue this analysis on the Bock boost topology next time. We are going to have the quiz now. So